Okay, it is 6:01, so I'm going to go ahead and get started. I see we have about half the normal amount of students as we usually have in the Zoom lectures. I'm assuming that's because of the hurricane coming. As I said in my email, I am perfectly fine with that. That is perfectly okay. If you need to leave this Zoom for your safety, please leave this Zoom. I am recording this. You can watch this at a later date. So if there is any concern with your physical well-being, etc., feel free to leave the Zoom at any time. But otherwise, I'm going to continue the lecture. I believe I should have power throughout this entire thing. It is not currently raining, knock on wood. It's not going to get too bad before this lecture ends. But if I disconnect, if anything happens, then the lecture is going to end there. That's how it's going to be. So let's go ahead and get started. I'm assuming everyone can hear me. If someone could just in the chat, just let me know if you're hearing me or not. I would greatly appreciate that. So just someone in, yep, I see someone said, yes, you can hear me. So that's wonderful. Thank you for saying that. I see 2 people, so thank you very much. All right, so today we are going to cover correlation. That's what the lecture today is about. But we're also going to discuss the midterm exam results. So as you got my email, okay. As you got my email, the midterm, y'all did a fantastic job. Y'all did an amazing job. We'll talk about that briefly. And then we're going to cover correlation, and then we're going to cover reliability. And somewhere in there, I have a few class notes about how we're going to handle the class moving forward. Nothing dramatic, nothing that different, to be honest, but I'll make a note about it. Okay, so first off on the exam, overall, everyone did extremely well. This is the highest class average I've ever had on the midterm ever. I think a large portion of this is because it was an open book, open note, take home, I guess take home, do wherever you want midterm, not mid-home. So y'all obviously took advantage of using your notes, and I'm completely fine with that. I'm completely okay with that. This is unprecedented times. I have never given an exam in this class before that has been online, that has been open note. So this was a learning experience for me. Even though this class average is higher than it probably should be, I'm not going to do anything about it. This y'all benefit from this. There is no downside for this for y'all. Even if class average is way too high for this class, there's nothing I'm going to change about it. So therefore, that's the class average. Y'all did really good, didn't obviously higher than I expected. I thought giving you 30 minutes less would possibly lower the grades more than usual, but this was about 6 to 8 points higher than the class average usually is for the midterm. So once again, good job. As you can see, this is the range of scores. There is a very clear, pretty clear bell shape. Once again, class average 92. Some people higher, some people lower. There was one outlier. If you're that person who is the outlier and you think something happened to your exam, please contact me. Please let me know if you think there was a mistake, because I went back, I double checked. It seems like that's what you got, but if you think that's wrong, please let me know. But otherwise, very clear bell shape, a little bit skewed because you can't get higher than 100, but that's what it looked like, so good job. Some quick notes about the exam. The midterm is, as you saw, there's a lot more multiple choice than I wanted. I told y'all it was going to be a lot of free response, but then when I was making the exam, it was just easier to make things multiple choice. There's a lot of questions where I was pretty much asking true or false, or pretty much asking, you know, 1 of 4 possible answers. And it was just easier to make it multiple choice than it was to have you type in true, type in false. You get the point. I hope no one minded that. Y'all got fine scores, so I'm assuming y'all were okay with that. Also, in general, with anything that was free response, I was pretty lenient. I recognize that these are interesting times, let's put it that way. So I was pretty lenient with answers. But honestly, it was about how I typically am most semesters. Most semesters, I'm pretty lenient with free response answers. With all that noted, take a look over your test. Make sure I graded everything correctly. There's always a chance I made a mistake. I've already had 2 people send me emails, and they weren't accusing me of making a mistake. It was more of just, hey, I got this wrong. I have no idea why. Can you tell me why I got this wrong? And I greatly appreciate that. That's always very nice as a professor to have a student send you an email saying, hey, can you just explain this to me? Always happy to explain things. Always happy to do that. Okay, so yep, so send me emails if you have any questions, etc., you get the point. Okay, And classes moving forward, from here on out, we're only learning various inferential statistics. So we've learned the building blocks, we've learned the basics of statistics in general, a lot of the basic theory behind it. So now we're going to learn how to do the statistics. Now we're going to learn how to do the inferential statistics. So from here on out, the first half of each class will be learning about the concepts. So the first half of this class will talk about correlation. What is it conceptually? What is it in practice? How do we use it? How do we understand it? How do we talk about it? And then the second half, you'll be performing the statistics on your own. You'll actually be running a correlation. You'll actually be calculating your Cronbach alpha today. The way I do that is in the first half, it's all lecture based like we have been doing. And then the second half, you use the guides that I sent you through email, and you'll actually do the statistics on your own following the guides. The reason why I do it this way is the first time I taught this course, I had everyone try to do it at the same time and watch me do it through lecture, and then y'all copied me. That worked out terribly. No one liked that. Everyone hated that. It's mainly because when it comes to statistics, everyone goes at their own pace. Everyone needs to go at their own speed. So when we try to do it together, you had some students who ran through everything super quickly, got to the end, and then had questions. And I had to say, no, back up. We have to wait for everyone. And then you had some students who, this is perfectly reasonable, this is perfectly fine, but struggled with things like finding the program on the desktop or figuring out how to open up a file. That's perfectly fine. That's perfectly understandable. But because of that, because there's such differing speeds, there's really no way to teach this with everyone trying to do it at the same time at the same pace. So therefore, how we do the lecture with the second half is you have access to the guides. You do the guides on your own. You go at your own pace. And then I'm here to answer questions. I'm here to help you out. So if you're going through the guide and you say, hey, Dr. Howard, I'm halfway through. I'm really stuck at this one part. I have no idea what's going on. That's when you can ping me through chat. If we're in person, you can raise your hand and I'll help you out with it. I'll give you assistance on calculating whatever you need calculated. I also tend to like that because that gives more one-on-one attention with students. So if you need one-on-one attention, I'm there for that. So that's how the class is going to go moving forward. Also, today is obviously online. As you got through email, Wednesday's class is canceled. So your class on Wednesday is canceled. I don't think I can give any type of makeup work for that. I don't think I can make you watch a lecture when that happens. Maybe I'm wrong, maybe who knows. But I think that it's just canceled is canceled. So therefore, don't worry about makeup work. You still have homework. You still have to do the homework. I'll double check on that. But as of now, you'll still have the homework. But I'm not going to make you watch a video. I'm not going to make you do any makeup work. Just Wednesday is canceled. We'll make up for that later in the semester. And I have classes built into the semester that are makeup days, that are catch-up days. That's perfectly fine. Also, I gave you all a survey asking you how you wanted the class format to be moving forward. So as you see, 14 students wanted 0, 1, or 2 classes in person, 7 wanted 3 classes in person, and 12 wanted 4, 5, or 6. So we still have this pretty uniform distribution, I guess, maybe bimodal, depending on how you want to look at it. So I know this still leaves 2/3 of the class somewhat unhappy, but we're still going to continue with Mondays in person, Wednesday online. I know that the students who want it to be entirely online aren't fully happy with that. I know the students who want it entirely in person aren't fully happy with that, but that's the only way I can think of that makes it a happy medium. So therefore, Mondays will still be in person, Wednesdays will still be online. Okay, with all that stuff noted, are there any questions about anything? Any comments about anything? Anything class related whatsoever that y'all have questions about? I'm now opening the floor for y'all to ask.
Will what's on our homework for this week be covered today, or do we need to watch like your supplementary videos that were already posted?
That is a good question. I believe the stuff on the homework is covered today. If it is not, then I will send an email with exactly what you need to know for that homework assignment. So I think what we'll cover today covers everything. If not, I'll send you an email, or worst case scenario, I'll push the homework due date back by a week. That would probably be the most likely thing if it turns out that you're not learning everything today. So good question. I will definitely, I'm writing that down right now so I don't forget. Homework. And I will send an email about that. Very good question. Okay, any other questions or comments?
Do we need Jamovi and Excel for today and moving forward, or are we fine with either or?
Very good question. So the question was, do you need both Excel and Jamovi? And the answer is yes, you do need both Excel and Jamovi. I think there's a chance you might only need Jamovi. I know there's at least one analysis that can only be done in Jamovi, so therefore you need at least Jamovi. Also having Excel would probably help.
And which version of Jamovi do we need to download? There's current and solid.
I always recommend the most recent version.
Okay.
If it's not working or if something seems weird with the most recent version, just let me know and I'll look into it.
All right, thank you.
Yep, good questions. Very good questions.
And there's never any like malware hiding behind this open source software, is there?
Sorry, say it again.
We don't have any like concerns for like malware since this is an open source software.
That's a good question. Not that I'm aware of with Jamovi. I've talked to the creators of it. I've talked to a lot of colleagues that use it at various companies. I'm not aware of any malware. Yeah, so I would say if you're concerned about it, let me know and I could try to find some type of alternative. But as far as I'm aware, everything I've read, everything I know about, Jamovi has no malware whatsoever. But if you're concerned, shoot me an email, let me know, and I'll try to think of something that would help with that concern. So, good questions. Any other questions or comments? Okay, going once, going twice. Okay, so let's go ahead and start the lecture. Okay, so as mentioned, today we're going to start inferential statistics. We're going to start with the very basic, the correlation, which is where most classes start by talking about inferential statistics. And we'll also talk about Cronbach's alpha today. So as you remember from before the midterm, inferential statistics infer relationships in our data. Inferential statistics infer relationships in our data. So our descriptive statistics just described our data, mean, median, and mode. Standard deviation, variance just describe the shape of our data. Inferential statistics infers relationships in our data. So it does more than just describing. It provides inferences regarding whether relationships exist among constructs or among variables in your data set. So a lot of different inferential statistics exist for a lot of different purposes. So in this class, we're going to cover correlation, regression, t-test, and ANOVA. If you're to enroll in the PhD program in the Mitchell College of Business, you would learn about things like structural equation modeling, multi-level modeling, latent class analysis, et cetera, et cetera. So from that, the big question everyone always has to start with is how do we know when to use each one? Is there one that's just better? Is there one that's just used for everything? And the answer is no. There is not one that's the best. There is not one that's better than all the others. Instead, we need to learn what these analyses do so we can also know what is the best situations we apply them in. When is the situations we should look and say, oh, I want to know the relationship between X and Y, I use a correlation. Or maybe I want to see the difference between group A and group B, that's a t-test. So we're going to repeatedly go back to this idea while we're learning inferential statistics is what are they used for? What are the situations that are they're best applied for? So therefore we can look at a data set and instantly know based on our research questions, what analysis should we use? Because there is no one best analysis. And also this is, I guess, a spoiler for the final. The final exam will probably be something like, here's a data set, and then I'll ask questions like, you need to find the relationship of X, Y, and Z predicting A. What analysis do you use? And then perform that analysis. Or maybe we have groups A, B, and C, compare their mean differences. What analysis do you use? And then actually apply that analysis. So for the final, there's a high likelihood I will not tell you what the analysis you should use is. Instead, I'll tell you the relationship you should investigate, and it's up to you to know what analysis to apply. And then I'll say this very briefly, is that most of the time on the final, students do really well. Most of the time on the final, the grading distribution is very similar to the midterm, but I do tend to have more students who get grades like 10s and 20s because they never really learn this. They never really review this, that they get to the final, they see me ask those type of questions and they think, oh gosh, I never learned when I'm actually supposed to use a regression. I learned what buttons to push, but I have no idea when to apply it. And you need to learn when to apply this type of stuff. Okay, so therefore in our class, we're going to remember when to use the basic inferential statistics as the very first question you should ask is, are you trying to explain the association between things or variables, the relationship between things or variables, the association between things or variables, or are you trying to explain the differences between groups? That's the first question you should be asking. So things that refer to the association, research questions that refer to the association between things or variables might be like, is there a relationship between someone's height and their GPA? That's the association between height and GPA. Or maybe like, is there a correlation between job satisfaction and job performance? That's an association between things. That's the relationship between job satisfaction and job performance. On the other hand, a separate category of research question involves the differences between groups. And these are some of the examples we've been using all semester. Maybe we're looking at the differences in productivity among factories, factory being the group, and then productivity being the outcome variable. So we're looking at the differences between groups, which were the factories, in regards to an outcome variable, which was performance. This was also, I think we used this example before. If you asked which class has higher test grades, is it Dr. Howard or Dr. Smith? That would once again be the difference between groups. The groups being the classrooms, and you're looking at the differences in their grades. So therefore, whenever you're trying to figure out what analysis you should use, you should first ask yourself, are you looking at the association between things or variables, or are you looking at the difference between groups? And then once you answer that question, you can get a better idea of the correct analysis to use. Okay. And this is a chart we are going to go through many times this semester. You will see this quite often. And this chart starts with exactly that. It starts by asking, are you explaining the relationship between variables, or are you looking at the difference between groups? So we're not going to go through this entire chart today, because by the end of the semester, we will have gone through this entire chart. We're going to go through parts of it, a new part each day. So today we're going to start by looking at, we are explaining the relationship between variables. That's where we're starting at today. We're starting at the relationship between variables. And then based on that, if you know you're looking at the relationship between variables, you should then ask yourself, how many variables are you studying? So once you've identified that you're looking at the relationship between variables rather than the difference between groups, you should then ask yourself, how many variables are you studying? That's the very first question you should ask. And the different options we have for this class, and let me say these are not the only options. There's different answers you could give to this question that would result in different analyses you should perform. However, the 4 options we'll look at to this question are either only two but controlling for others, many predictors, one outcome, or many predictors, many outcomes. So to start, we're looking at only 2 variables. We're looking at only 2 variables. So for today, we're looking at the question, how many variables are you studying? The answer is only 2. So to put it all together, today we're looking at when we're explaining the relationship between variables, and then when we ask ourselves, how many variables are we studying when we're looking at these relationships? The answer is only 2. We're only looking at the relationship between 2 variables. And then based on that, we know that we should perform a correlation. When we're looking at the relationship between variables, and we're only studying 2 variables, we're looking at a correlation. We're going to be using correlation. And hopefully by the end of the semester, this type of thing should become automatic for you. This should become automatic. That when I give you a data set and I say, look at the relationship between job satisfaction and job performance, you should instantly click and say, all right, that's a relationship question. That's only 2 variables. Therefore, I need to perform a correlation. Okay. So let me clear all that and let's continue. Also, you saw these analyses in the chart that we just looked at, and this is just a note for you as we move throughout the semester. We're going to be learning about these topics in the following order. So we're going to be learning about correlation and reliability today. Our next lecture is going to be about partial correlation and regression. The lecture after that will cover probably dummy coding and advanced regression, hopefully, assuming we don't lose too much time. Then we're going to cover t-test, followed by ANOVA/chi-square, And then we're going to conclude the semester possibly with prediction, maybe using R. I kind of doubt we're going to use R, but maybe. And then also just catching up on things if we need any time to catch up on things. So if you want to go back and look in that prior chart, just to get an idea of, all right, here's the names of the analyses. When do we use it? What are their differences? You could go ahead and get a head start on that if you're really motivated to do so. You can go ahead and look at that chart and identify, well, what's the difference between a correlation and a t-test? What type of research questions would I answer with a correlation? And what type of research questions would I answer with a t-test? You don't have to do that. That's up to you. It's available if you want to do it. But by the end of the semester, that chart should become automatic to you. Okay, with all of that noted, we're going to start by talking about correlations. I'm assuming most of y'all have been exposed to correlations before to some extent, and that's perfectly fine. It's also perfectly fine if you have never heard of a correlation before in your life. We're going to start with the basics. One question in the chat was, are we assuming a normal distribution for our data for all the analyses? The answer will be yes for most of them. So correlation, regression, t-test, ANOVA are going to assume a normal distribution. Chi-square test doesn't necessarily assume a normal distribution. Chi-square test doesn't automatically assume it. And then also when we do advanced regression, depending on how much time we have, we might learn certain regression techniques that do not necessarily assume a normal distribution. We might learn some regression techniques that might allow for other distribution assumptions. But the short answer is yes, we will assume the normal distribution for most analyses, but not all of them. So very good question down there. Okay, any other questions at this point? Okay, so I'm going to continue. Okay, so what is a correlation? What is a correlation? So a correlation is used to determine the linear relationship between two variables. A correlation is used to determine the linear relationship between two variables. So as you see, it's looking at relationships, like we talked about before. It's looking at two variables, like we talked about before. But the new piece of information in this definition is that word linear, and that's extremely important. And we will talk about that in a few minutes. But it's used to determine the linear relationship between two variables. And don't forget about that linear part. Some examples of when we might use correlation might be looking at the relationship between job satisfaction and job performance. So that's two variables. And we might just want to look at the linear relationship between those two variables. Another important question might be, what's the relationship between sales and revenue? We would probably expect an extremely strong correlation between those two because we would expect those two to be very strongly related, but we could still measure them. That would be two variables, sales and revenue. And then we could calculate the linear relationship between those two variables to get an estimate of how related they are. Okay, and then the last example is, what's the relationship between ad spending and sales? And this would be more common for a business analysis. That we might look at a lot of different companies. We might ask them, how much do you spend on ads? And then how many sales do you make per year, month, whatever? And then we might correlate those two. So we can get some type of estimate of, do ads really pay off? Are ads really worth it? Should we be spending more on ads? Should we be spending less on ads? And this is the type of data-driven decision making we should be using. And we can use correlation to help with that data-driven decision making. Okay, so this is a visual representation of a correlation. This is what a correlation does conceptually. As you can see, this is a scatter plot. As you can see, this is a scatter plot. And we have each of our individual observations here on the scatter plot. So right here, the one I just circled, we can see this person has a job satisfaction score of 3 and a job performance score of 2. This next one I circled, we can see that is a job satisfaction score of 2 and a job performance score of a 5. And then so on and so on. This one is a job satisfaction score of 6 and a job performance score of 10. So one way to think about correlation, what a correlation does, is imagine if you plotted all of your values on a scatter plot, and then you drew the line of best fit, which is this dotted line right here. And then you drew the line of best fit. That is pretty much all a correlation does. It just does it numerically. It just does it with numbers. One way to think about it is a scatter plot, and then your correlation draws the line of best fit. Your correlation tells you, what is the best way to describe this relationship? What is the best way to describe this relationship? wherein this line is the closest line to all of these values. That if you were to draw any other line on this chart, it would have a greater total distance away from all of these individual points. So as you can see, this line does have some deviations. This line does have some deviations. Almost no correlation will be perfect. Almost no correlation will be perfect unless you're in the hard sciences and you're measuring things like gravity. Yes, gravity is going to give you perfect correlations for certain things you might want to measure with it, or some certain things you might want to look at. But especially for the social sciences, no correlation is going to be perfect. You're going to have some deviations. However, with a correlation, if you were to draw any other line here, let's just say hypothetically we were to draw this line right here, the deviations, or the distance between this line and all the points, would be greater than what was estimated by our correlation. The distance between this line that we just drew, or any other line you could draw, would have a greater deviation from that line and all of the points than the original correlation line, than the appropriate correlation line. So therefore, this correlation can be thought of as an indice of best fit. It draws the line of best fit, and it gives you the estimate of the relationship that best describes, or sorry, it gives you the estimate of the correlation that best describes the relationship between those two variables. So once again, in very short, one way to think about a correlation is it gives you an indicator of the relationship between the two variables, and it gives you the line that best summarizes that relationship. It gives you the line that best summarizes that relationship, and it does it numerically. We'll talk about how the numbers from a correlation relate to the lines. Okay, so let's clear that. So quick question for the class. Hopefully there's some people that are able to answer this. If you were to look at that line right there, do you think this correlation would be positive or negative? Is this line that you see on the screen right now describing a positive or negative correlation? Yep, I see one person. I saw tons of people in the chat. So good job. I'm glad you are familiar with correlation. Give yourself a pat on the back. This would indeed be a positive correlation. This would indeed be a positive correlation. Because in this example, we see that as job satisfaction goes up, job performance also goes up. That as this line gets larger in regards to job satisfaction, it also gets larger in regards to job performance. So therefore, whenever you're working with correlation, if you have a line that has a slope like this, if you have a line that has a positive slope, therefore that means there's a positive correlation between the two variables, that as job satisfaction goes up, job performance also goes up. So this means it's a positive correlation. All right, here's another example. So as you see in this one, pretty much the same thing. We're looking at self-esteem and job satisfaction. We have these individual points, and we see that the line goes down. And I see one person in chat already answering my question. Good job, Whitney. That we see this already goes down, that as self-esteem goes up, that is the numbers related to self-esteem get higher. As self-esteem goes up, job satisfaction goes down. Job satisfaction goes down. So from this, we can see, because this line has a negative slope, this indicates a negative correlation, that as one variable goes up, the other one goes down. And we see that if you start with self-esteem of 0, job satisfaction of 12 on the line. Once we go to self-esteem of 1, job satisfaction is about an 11. Self-esteem of 2, job satisfaction is about a 9.5. Self-esteem of 3, job satisfaction is about a 8.25, and so on and so on. So therefore, a negative correlation is when one variable goes up, the other goes down. That is a negative correlation. And you can think of it as a line with a negative slope, a line that goes down like this. Okay. So moving forward. All right, so this one is a hard one. What type of correlation would this be? Is this positive, negative? Yep, I see one person in the chat already answering the question, so good job on that. This would be no relationship. This would be no relationship that we see as conscientiousness goes up. There's no change in job performance. There's no change in job performance. That it doesn't matter if your conscientiousness is a 1, a 2, a 3, a 4, a 5, a 6, or a 7. It doesn't matter. Your job performance stays the same. So a line that's completely flat means there's no relationship. So once again, a line that is completely flat, that means there is no relationship. And it doesn't have to be, as I've illustrated right here. It doesn't have to be all the lines fall on, or sorry, all the dots fall on the line. You might have a no relationship. Let me see if I can get a bigger draw tool. Give me one sec. Does this work? There we go. It could look something like this, is we could have a bunch of random points that kind of make a circle, or I guess a diamond that I ended up drawing because I'm really bad at drawing and I guess I can't draw a circle. And if you were to draw the line of best fit right here, it would probably look something like that. And imagine that's a flat line. That would also indicate that there's no relationship between conscientiousness and job performance. Because even though we try to draw the line of best fit, the line of best fit in this example is completely flat. The line of best fit in this example is completely flat. So therefore, it doesn't matter what your conscientiousness is in this example, it's still estimated that your job performance would be the same. It's still estimated that your job performance would be the same. So it doesn't have to be all the points falling on the line for it to be no relationship. You could have something that looks like this where you have points all over. It's just the line of best fit is still completely flat. It's still the line of best fit is completely flat. And that would still indicate no relationship. Okay. Any questions about that so far? Any questions about this so far? Okay, so moving forward then. Okay, so this is just for your knowledge. I actually am not going to expect you to know these formulas, but this is just for your knowledge. To calculate a correlation, you would first need to calculate the covariance. You first need to calculate the covariance, and this is the formula for covariance. And you know enough about statistics at this point that you should be able to look at that formula and say, oh, that's really easy. I could do that by hand if I wanted to. And I've taken classes and I've calculated that where I've had to calculate that by hand before. It's easy. It's not that difficult. It just takes time. I don't think you learn a lot from it. But if you're the type of person who learns better by doing, try it yourself. Find a very simple data set. Find an easy data set that maybe has 8 observations and see if you can calculate a covariance by hand. As you see, it's the sum of all the x values minus the mean of x times their respective y values minus the mean of y, and then divided by the sample size minus 1. And that gives you covariance. But a covariance is not a correlation. So therefore, to get the correlation, you take your covariance and you divide it by the standard deviation of x times the standard deviation of y. So it's just the covariance divided by the standard deviation of x times the standard deviation of y. And this standardizes your covariance. This standardizes your covariance. Whereas covariance could have very differing results depending on how you measured your variables. Covariance can have very differing results no matter how, or depending on how you measured your variables. On the other hand, correlations are standardized. If you look at a correlation and it says 0.4, you're going to know that's a pretty strong correlation no matter what you're looking at, no matter what you measured. Within reason, we'll talk about nuances to that in a little bit, but generally a correlation of 0.3 is a correlation of 0.3 is a correlation of 0.3, that they're generally going to represent the same strength of relationship. However, a covariance of 0.3 might be different than a different covariance of 0.3, because a covariance does depend on your unit of measurement. Whereas a correlation is standardized, a correlation, we can much more easily look at it and quickly know, all right, what type of relationship is it describing? What strength of relationship is it describing? And what direction of relationship is it describing? So that's why we tend to report the correlation instead of covariance, because it's much easier to interpret. Statistics is all about interpretability, and that's why we like correlations. Okay. Also, other things you should know is we call R the correlation coefficient, and this is the test statistic from a correlation. So we talked about this in class a little bit before, is if you ever see something like R equals 0.1, if you ever see something like R equals 0.1, then you know that that's referring to a correlation. You know that's referring to a correlation because we call we call the correlation coefficient R, and vice versa, we call R the correlation coefficient. So if you ever see something like R equals 0.1, they're just saying that the correlation between whatever two variables they're looking at is 0.1. And this is the test statistic from a correlation. Another thing you should know is we call R squared the coefficient of determination. R squared is the coefficient of determination. And R squared is quite literally your correlation squared. It is quite literally your correlation squared. So in that prior example of 0.1, if your correlation was 0.1, that means your R squared is 0.01, because 0.1 times 0.1 is 0.01. And we call that the coefficient of determination. The coefficient of determination is the percent of variance that is shared between two variables. So that just gives you an estimate of how much variance do these two variables share. And that's very similar to a correlation. We'll get more into this once we get into regression, because regression also has a very similar concept. In fact, it has an identical concept. So we'll talk about this a little bit more when we get to regression, but just think of it as how strongly related those two variables are. And typically, if we get an R square of, let's say, 0.01, we could then say that not only does job satisfaction share 0.01% of the variance in job performance, but if we're assuming that X predicts Y, we can also say that's the percent of variance in one variable that's predicted by the other. So if we satisfy the rules of causality, which we'll talk about in the regression lecture, if we satisfy those rules of causality, then we can say that our R squared tells us how much of the variance in the outcome is explained by that predictor. How much of the variance in the outcome is explained by that predictor. That doesn't mean that if you have an R square of 0.01, that doesn't mean that we can guess what the value is of the outcome 1% of the time. It does not mean that. Instead, it just means that we can, that the variance in that outcome, that 1% of that variance can be explained. That if we were to use the results of this relationship, we could hopefully be able to predict a certain portion of that variance. And if it's a causal relationship, maybe even manipulate a certain portion of the variance. It doesn't necessarily mean that we can suddenly predict it 1% of the time or anything like that. It just means that we know some type of estimate of how much of the variance in that outcome is indeed explained by the predictor. Okay. Oops, I need to clear the screen. All right, other things you should know about correlation is correlations can range from -1 to 1. So correlations can range from -1 to 1. Negative values indicate a negative relationship, and positive values indicate a positive relationship. So like we were looking at before, negative relationships look like this with a line that goes down. Positive relationships look like this with a line that goes up. So these are negative relationships and these are positive relationships for correlation. And then once again to the class, or here's a question for y'all. What number represents no relationship? What number represents no relationship? Going once, going twice. There you go. Good job. Oh man, we have like 5 answers. Good job. So y'all are doing really well. Yes, you're correct. That 0 means no relationship. That if we have a result that says our R equals 0.00, that means that there's no relationship. That means there is no relationship between those two variables. And once again, that is a flat line. That is a flat line. So flat line is no relationship, and that would be something like R equals 0.00. That's no relationship. Okay. Other things to note, there we go, is values farther away from 0 are stronger. And this is very important to know. Values further away from 0 are stronger. So therefore, we have negative numbers, we have positive numbers, and how to interpret their magnitude, how to interpret their strength is their distance from 0. So therefore, we might have a correlation. Where's my text tool? There we go. We might have a correlation of R equals 0.20, and that's a moderate relationship. That is a moderate relationship. However, a correlation of -0.20 is also a moderate relationship. It's just the first one. 0.20 is a moderate and positive relationship, whereas -0.20 is a moderate and negative relationship. -0.20 is a moderate and negative relationship because it's all about their distance from 0. It's all about their distance from 0. And then also to give another example, and we'll talk about this more in depth, I think on the next slide, maybe in 2 slides, is if we have a correlation of, let's say, R equals 0.20, and another one of, let's say, R equals -0.40, Can anyone tell me which of those two would be stronger? Which of these two do we consider to be a stronger correlation? Yep, exactly correct. I see someone in chat got it, so good job. Exactly correct. We would consider negative 0.4 to be the stronger relationship. We would consider negative 0.4 to be the stronger relationship because this is the one that's further away from 0. Negative 0.4 is further away from 0 than 0.2, so therefore we say that's the stronger relationship. So it's all about magnitude. It's all about the magnitude of results. Okay. And then I think it's the next slide. Let's see. Yep. So on this slide, I'm going to give some examples and y'all tell me the answers. So first off, which of these correlations is stronger? Is 0.1 or 0.3 a stronger correlation? Yep, that's correct. That is correct. 0.3 is the stronger correlation. So good job on that one. All right, next one. Is 0.2 or 0.7 the stronger correlation? Yep, 0.7, good job. All right. Is negative 0.3 or negative 0.1 the stronger correlation? Yep, negative 0.3. Is negative 0.3 or 0.5 a stronger correlation? Yep, 0.5, y'all are on fire, good job. Okay, negative 0.5 or 0.3? Yep, negative 0.5. And then negative 0.15 or 0.15? Yep, there you go. Both or neither would be correct answers. These are equal. These are equal in magnitude. Both of them are strong, or both of them are equally strong. Neither are equally strong. So they have an equal relationship. Not an equal relationship. They have a relationship that's equal in magnitude. It's equal in magnitude. So good job. Good answer on that. Those are equal in magnitude. Okay. So good job answering all of those. One thing that you might have asked already is, all right, we have correlations. They can range from -1 to 1. How do we know what is a small, medium, and large relationship? So if you're reading an academic article or you're looking at a business report and you see a correlation of -0.3, 0.17, 0.78, -0.44, how do you know if those are small, medium, or large? How do you know? Are you supposed to be impressed by that? Or are you supposed to say, oh gosh, we know nothing about that outcome? And the answer is, it depends on your field. It depends on your field of study. So for instance, in the hard sciences / engineering, we generally expect really large correlations. In the hard sciences or engineering, we generally expect really large correlations. And that's typically because we're looking at physical properties of things. We're looking at physical properties of nature. So if we're looking at how much force can a building withstand, typically we can say, all right, well, we'll look at these certain properties of cement, for example. We can estimate which ones would be stronger, which ones are weaker, and then we can correlate, all right, well, let's look at the correlation between what we put into the cement versus how much strength it could withstand. And you're going to get large correlations because you're looking at physical properties of nature. Also, in certain parts of, let's say, engineering, and this is even a business example, is if you're looking at something like developing a product production process and you want to analyze the relationship between the quality of inputs and outputs, the correlation is probably going to be pretty large because you can hold everything else constant. One of my colleagues at South Alabama, he used to work for a company where he just looked at conveyor belt layouts and looked at things like, all right, if we move these products quicker through the conveyor belt, slower, if we have certain parts where the product has to be heated up, if we heat it up for 1 minute versus 2 minutes versus 3 minutes, are we going to get more or less effects, et cetera, et cetera? He was dealing with extremely large correlations because he could hold everything constant and then just change one little part of the process. And once again, it was a physical part. It was something you could easily observe and easily know, all right, well, here's what we would expect it to be, measure the outcomes, and he would get large correlations. However, for a lot of the parts of business and also the social sciences, we would expect much smaller relationships. We would expect much smaller relationships because in the social sciences and a lot of parts of business, we're dealing with people. People are very unpredictable. People are very hard to predict. Whereas in something like physics, we could look at the trajectory of stars. We could look at how things fall to the ground and look at gravity and try to estimate their trajectories and calculate statistics based on that. And you would get really high, strong relationships and correlations. In the social sciences, people are much harder to predict. People are much harder to know what they're going to do or what they're not going to do. And it's honestly one thing that really drew me to learning more about statistics and applying them to business is because I'm really fascinated by this idea of applying statistics in instances where you have very large errors. You have very large errors in your analyses because people are so hard to predict. You have no idea what's going to happen. So therefore, we have to figure out how to perform statistics, but also how to invent statistics that can deal with that error, that can deal with that much variation in your observations. So for instance, when studying the relationship between job satisfaction and job performance, a lot of external factors might influence this relationship, and we cannot keep everything constant. So therefore, if we're looking at just measuring job satisfaction and just measuring job performance, we might get a pretty small correlation because there's so many other things that predict job satisfaction that we're either not measuring or we cannot measure. So therefore, we might get pretty small correlations in the social sciences. We'll look at things like that. Also, this is another example, and I'll keep it brief, but the entire field of personnel selection, that's what that field is about. This question is what that field is about. Is personnel selection is all about how can we maximize our R squared in regards to employee performance by altering our selection processes. There's tons of error variance in that. There's tons of error involved when it comes to personnel selection. I feel like every few years there's someone who comes out with a huge report where they try to claim, oh, I made the best personnel selection tool that's ever been invented. I can predict employee performance to this remarkable number based on a very small number of predictors. And then every time it turns out to be they did their analyses wrong, or that they included something in their analysis that probably shouldn't have been there. So once again, if you're interested in this type of question of predicting outcomes when you have a lot of variance, predicting outcomes when you have a lot of error involved, personnel selection might be for you. Personnel selection might be the thing that you get really interested in. If you are interested in it, let me know. I can give you some books, I can give you some articles. There are major breakthroughs being made every single day in the field of personnel selection. Okay, so what are we going to use for this class in regards to small, medium, or large? How are we going to consider our variables to be small, medium, or large in this class? And the answer is we're going to use Cohen's guidelines that he invented in 1992. So what Cohen did in 1992 is he reviewed a lot of the journals in the social sciences, a lot of the academic articles in the social sciences, and he categorized them and said, all right, on average, this was the distribution of correlations from these articles. And this is what I would consider small, medium, and large based on what's been previously published, based on what's already out there. And Cohen in 1992 suggested for the social sciences that a correlation of 0.1 is small, a correlation of 0.3 is medium, and a correlation of 0.5 is large. And that's what we're going to use in this class, is if your correlation is about around 0.1, so if it's 0.05, if it's 0.15, if it's 0.1, that's small. Something around 0.3 is medium. If it's 0.25, 0.3, 0.35, that's medium. And then if it's around 0.5, that is large. So if it's 0.45, if it's 0.55, we would consider that large. And once again, that's based on Cohen's 1992 recommendations that he based on reviewing the existing literature and said, all right, here's what prior people have found. I categorize these into small, medium, and large into equal size categories. And here's what I think we should use moving forward. Just for your knowledge, Cohen has been the guidelines people used almost exclusively in the social sciences for about 25 years. Is that right? Yeah, about 25 years. And then I think it was 2017. There's been 3, maybe 4 now new articles that did exactly what Cohen did, but just did a more systematic approach, used meta-analyses, which Cohen did it more based on a systematic literature review approach. These new articles have done it through a meta-analysis approach. And there are some slightly different guidelines that academic articles use now, but a lot of people still base their guidelines on Cohen. A lot of people still use this 0.1 small, 0.3 medium, and 0.5 large. And this is especially true if you're in management, if you're in marketing, because you're dealing in the social sciences. A lot of researchers and practitioners, especially practitioners, still use Cohen's guidelines, especially if you're in management or marketing. Okay. And then the last one you should be aware of is for anything above 0.7, you should start to wonder whether you're measuring the same thing twice. Anything above 0.7, any correlation above 0.7, you should start to wonder whether you're measuring the same thing twice. That's not always the case. That's not always what happened, but you should at least wonder it. One example of this is, let's say there's two separate constructs that people have studied in research, and it's often discussed in practice, is we might have job satisfaction, but there's also a construct of organizational-based self-esteem. And it's how you feel about your self-worth in the context of your company. How good do you feel about yourself when you're at work? And that's called organizational-based self-esteem. If someone were to study those two concepts, job satisfaction and organizational-based self-esteem, they would first have to show that the correlation between those two is below 0.7. They would have to show the correlation between those two is below 0.7. Because if you correlated those two and you got a correlation of something like 0.9, then now it suggests that, hey, organizational-based self-esteem is just job satisfaction with a new label slapped on. It's just job satisfaction, you're calling something different. And therefore, you're not studying anything new, you're not studying anything that's novel, you're just studying job satisfaction and calling it something else. So therefore, if we have a correlation that's above 0.7, you should start to wonder whether you're measuring the same thing twice. That's not a guarantee that you are, but it's a consideration you should make. Okay. And then also, therefore, we're going to use these benchmarks in this class because they apply to organizational behavior, management, marketing, et cetera, But if you're in other aspects of business, such as econ, accounting, you're probably going to have other correlation benchmarks, and you should reach out to your professors of those classes to determine what are the correlation benchmarks for those fields of study. You should definitely reach out if that's the type of thing you're interested in, because these are the correlation benchmarks for management, marketing, and other similar fields. Okay, so based on that entire explanation, what would you say about these following correlations? So how would you describe a correlation of 0.3? Yep, I see people saying it in the chat, and you're correct. You would say it's medium, and then you would also say it's positive. So you would say if you got a correlation of 0.3, that you had a moderate and positive relationship between those two variables. You had a moderate and positive relationship between those two variables. So good job, I see. Yep, everyone in the chat got that, so good job. All right, so let's say we had a correlation of about 0.4. Let's say we had a correlation of 0.4. What would you say about that one? Okay, yep, so first off, everyone said positive, so that's good. And I saw a mix between medium and positive and large and positive, and that's because it falls right in between those two benchmarks of 0.3 and 0.5. So if you have something like 0.4, you could say it's moderate to positive. You could say it's moderate to positive, because it falls right in the middle there. That in this instance, I would probably say that we found a, sorry, if I was saying moderate to positive, which I think is what I was saying, I think I meant to say moderate to large. I meant to say moderate to large. That if you had a correlation of 0.4, you would say it's a moderate to large correlation, and you would say it's a positive correlation. So therefore, if I were reporting this in an academic article or a report I wrote up for a company, I would say that we found a moderate to large and positive correlation between those two variables. So once again, moderate to large. All right, what about this one? How have we described this one? So first one is negative, that's correct. First one is negative. One person says negative and small. One person says small to moderate negative, and yeah, I think y'all got the point. Personally, I would say this is small to medium, small to moderate. I think someone in chat asked about that. You could use either or, mediate or moderate. If you're describing correlations, saying medium or moderate would be fine. And in this case, I would say it's a small to moderate or a small to medium correlation, and it's negative. So small to moderate and a negative correlation. Okay, and then what about this one? What would you say about this one? Exactly, questionable and positive. I like how that's worded. Questionable and positive, that's correct. Is that we would start to wonder whether we're measuring the same thing twice if we have a correlation this strong. So we'd probably say questionable and positive, or you could say it's extremely strong and positive, or very strong and positive. Extremely strong, questionable, and positive, you get the point. Okay, and this was the last one, and I'll go ahead and give the answer. Actually, I have another one after this, but for this one, negative 0.15, I would just say it's small and negative. That's pretty close to 0.1. 0.15 is pretty close to 0.1. I would say that is small and negative. So negative 0.15 is small and negative. Okay, and then what would y'all say about this one? What would y'all say about this one? Yep, so one person says very small, so I think that would be appropriate, negative and very small. I would also think it would be appropriate to say virtually no relationship, because that's so close to zero. Yeah, that's a good way to put it. Little to no relationship. One person in chat said little to no relationship. And I think that's a wonderful way to put it. If I had something this small, if anything's below 0.05, if anything is below 0.05, I would start to say little to no relationship. That's a wonderful way to put it. Okay. All right, so from all this, you now understand correlations, what they mean in general, what they mean, how to interpret them. You also know what's small, medium, and large, positive or negative. So now you probably asked, all right, how does hypothesis testing work with a correlation? How does hypothesis testing work with a correlation? And we will cover that. So when performing a correlation analysis, our null and alternative hypotheses are typically, so our hypothesis, which is also called the alternative hypothesis, so our hypothesis, which is also called the alternative hypothesis, is typically a significant relationship exists between job satisfaction and job performance. So our hypothesis is just some type of relationship exists. Some type of relationship exists between job satisfaction and job performance. So therefore, we hypothesize the relationship between the two variables is anything other than zero. Anything other than zero. Even though we might be interested in whether it's positive or negative, even though we really want to know whether it's positive or negative, we're not going to be that specific with our hypothesis. Instead, we're just going to hypothesize that there's some type of relationship that R does not equal zero. So therefore, based on that, based on hypothesizing that very general hypothesis, the implied null or the null hypothesis whenever you're running a correlation is simply no relationship exists. The null hypothesis is simply no relationship exists between job satisfaction and job performance. So therefore, the null hypothesis is simply R equals zero. The null hypothesis is simply R equals zero. And that means that no relationship exists between the two variables you're looking at, in this example, job satisfaction and job performance. So once again, our hypothesis or the alternative hypothesis is that the correlation is anything other than zero. The null hypothesis is the correlation is zero, the R equals zero. So therefore, based on that, we perform a correlation analysis to determine whether we can reject this null hypothesis. We perform a correlation analysis to determine whether we can reject this null hypothesis. And to do that, we use p-values and /or confidence intervals to do this. So we would use p-values or confidence intervals like we learned before the midterm to do this, to determine whether we can reject the null. So therefore, for a correlation, a p-value would tell us, assuming there is no relationship between these two variables, what's the likelihood of obtaining our observed results? So assuming the null hypothesis is true, so assuming there is no relationship between these two variables, what is the likelihood of obtaining our observed results? So that's what a p-value would tell us. So it's very possible we would get a result that might look something like R equals 0.22, P equals 0.03. And all that says is there would be, assuming the null hypothesis is true, if we're assuming that a whole null hypothesis is true, there was only a 3% chance, of observing that correlation of 0.22. So once again, assuming the null hypothesis is true, there was only a 3% chance in this example of observing your correlation of 0.22. And that's what a p-value tells you in the context of correlation. Also, if our p-value is small, so if the p is less than 0.05, we can reject the null hypothesis. So if your p-value is small, we can reject the null hypothesis. And in other words, you're saying that our results are likely due to more than random variance alone. There's some type of meaningful relationship between those two variables. If you can reject the null, if your p-value is small, which means it's less than 0.05, you can say that your results are due to likely more than random variance alone, and that your relationship has some type of meaningful, or sorry, the two variables you're looking at has some type of meaningful relationship between them. And I see someone asked in chat, can we say we fail to reject the null if the correlation is less than 0.05? So when we're talking about null hypotheses and whether we can support or not support our hypothesis, we're only looking at the p-value. So the correlation helps us interpret the relationship. However, it's the p-value that lets us know whether we can reject the null hypothesis and therefore support our hypothesis. So when we're talking about hypothesis testing, we're only looking at the p-value. Our correlation helps with interpretation of the relationship, but hypothesis testing is all about the p-value. And then if your p-value is less than 0.05, if your p-value is less than 0.05, you can reject the null. If your p-value is less than 0.05, you can reject the null. However, if your p-value is greater than 0.05, you fail to reject the null. If your p-value is greater than 0.05, you fail to reject the null. Because in that instance, if your p-value is, let's say your p-value is 0.17, that means there was a 17% chance of observing your results, assuming the null hypothesis is true. So in that instance, 17% chance, that's pretty high. A 17% chance is pretty high. So in this instance, you're saying, well, that's a pretty high chance. Therefore, we cannot reject the null. Therefore, since it's had a pretty good likelihood of observing our results, assuming the null is true, that's a pretty good chance. We cannot reject the null. So therefore, we would fail to reject the null. Therefore, we would fail to reject the null because our p-value was greater than 0.05. So once again, if your p-value is less than 0.05, you can reject the null. If your p-value is greater than 0.05, you fail to reject the null. You fail to reject the null. So very good question on that. Okay, so to wrap it all up once again, whenever you calculate a correlation, you get your correlation coefficient, which is used to interpret the relationship, but you also get a p-value, which is used for hypothesis testing. You also get your p-value, which is used for the actual hypothesis testing. If your p is less than 0.05, if your p is less than 0.05, you can reject the null. You can reject the null if your p is less than 0.05. So that means that you support your hypothesis. You support your hypothesis if your p is less than 0.05. However, if your p-value is greater than 0.05, if your p-value is greater than 0.05, you fail to reject the null, and therefore you do not provide support for your hypothesis. If you fail to reject the null, you do not provide support for your hypothesis. Okay, so based on all that, are there any questions about hypothesis testing with correlations at this point? Any other questions about hypothesis testing with correlations at this point? Going once, going twice. Okay. So to continue, we can also calculate confidence intervals. And as you remember with confidence intervals, the confidence interval would tell us the reasonable range we would expect the population correlation to include or to be within. A correlation confidence interval would tell us a reasonable range that we could expect the population correlation to be within. So I don't think I have any examples on this, but one example might be that I'll just make up right here, is we might calculate a correlation of 0.3, and then we can also get a 95% confidence interval of, let's say, 0.20 to 0.40. And all that would say is that our correlation is 0.3. However, the reasonable range we could expect the population correlation to be within would be 0.2 to 0.4. That even though our observed correlation is 0.3, the expected, or the range we could expect the population parameter to fall within would be somewhere between 0.2 and 0.4. Because we know that our observed correlation is not perfect, we know that our sample is not perfect, so therefore we calculate a range that we might expect the population correlation to fall within. Once again, this range is not perfect, this range might be wrong, but it's a good guess, it's a good estimation. And as you hopefully remember about confidence intervals, if this range does not include 0, then we can reject the null. Because once again, the null is 0. The null is a correlation of 0. So 0 falls outside of that range. If 0 is outside of that range, then we can reject that as a plausible explanation. We can therefore reject the null hypothesis. So question for the class, based on this result I just calculated, can we reject the null hypothesis based on that result we just calculated? Yep, I see someone jumped on that extremely quickly. Good job. So yes, we could reject the null because this range, 0.2 to 0.4, that does not include 0. That range does not include 0. So you're saying if this was your result, 0 is not a plausible explanation for your population parameter, so you can reject 0. You can reject the null hypothesis because 0 is not a plausible value for your population parameter in this example. Okay. Any questions about confidence intervals then? Any questions about confidence intervals? Going once, going twice. Okay, I'm going to move on. If you do have any questions, type them and I'll answer them as I see them. Okay, and I think this is the last thing I want to say about correlations, I think, is that often we present correlations in a correlation matrix, and this is something you certainly should be familiar with. You certainly should be familiar with. This correlations are almost always presented in a correlation matrix. And a correlation matrix looks like this. In this correlation matrix, we have 4 variables, and we have the correlations between each of those variables, which is 6. We have 6 correlations because we report the correlations between each of those variables. How you read a correlation matrix is you have the row. Each of the rows has a different variable, and the columns correspond to the rows. The columns correspond to the rows. So as you see, the first row is job satisfaction, and that's numbered number 1. So therefore, this column also corresponds to job satisfaction. The second row is job commitment. That is row number 2. So therefore, the second row corresponds to job commitment. Intrinsic motivation is number 3. Intrinsic motivation is the 3rd row. So therefore, intrinsic motivation is the 3rd column. And job performance is the 4th row. So therefore, job performance is the 4th column. So based on this, we can see what the correlations are between each of those variables. And how we do that is we start and see where the column intersects with the row. We see where the columns intersect with the row. So the very first column, as we just said, is job satisfaction, because job satisfaction is number 1. So we can go down and see where does the first column intersect with the rows. So the very first one is column number 1 intersecting with row number 2. So this right here would be where job satisfaction correlates with job commitment, where job satisfaction correlates with job commitment. Because this is the job satisfaction column, this is the job commitment row, and we see that there's a 0.42 there. So from this correlation matrix, we can automatically know that the correlation between job satisfaction and job commitment is 0.42. So we would know that there is a moderate to large and positive correlation between job satisfaction and job commitment. And we see that because this is the job satisfaction column, and we see where it intersects with the job commitment row. And we see that that's a 0.42 right there. So that's the correlation between job satisfaction and job commitment. You'll also see that there's these asterisks right there. You'll also see there's these asterisks, and that represents the p-value. That represents the p-value. Typically, when you're looking at a correlation matrix, 1 asterisk means that the p was less than 0.05, so it was statistically significant if there's 1 asterisk, and 2 asterisks means the p was less than 0.01, and that also means it's statistically significant. So therefore, typically, when you're looking at a correlation matrix, any asterisk next to a number means that it's statistically significant, and the number of asterisks indicate how small that p-value was. So once again, if you see any asterisk next to a number in a correlation matrix, that typically means it's statistically significant. That correlation was statistically significant, and the number of asterisks tells you how small that p-value was. So in this example, between job satisfaction and job commitment, we see there's 2 asterisks. So we know that that correlation was statistically significant, and the p-value was in fact less than 0.01. The p-value was in fact less than 0.01. Okay, we can look at the next example. The next example is the job satisfaction column intersecting with the intrinsic motivation row. So the next example is the job satisfaction column, the first column, intersecting with the intrinsic motivation row. And we see that the number there is 0.37. So therefore, there is a 0.37 correlation between job satisfaction and intrinsic motivation. And we see there's 2 asterisks, so we know that result is statistically significant. Then once again, the next one is the job satisfaction column with the job performance row. We see that the correlation there between job satisfaction and job performance is 0.09, and we know that's a small relationship. So we would say there's a positive and small relationship between job satisfaction and job performance. And as you can see, there are no asterisks here. As you can see, there are no asterisks here. So that means that the associated p-value with that correlation, was greater than 0.05. It was greater than 0.05. So that means that the correlation between job satisfaction and job performance was not statistically significant. The correlation between job satisfaction and job performance was not statistically significant. Okay, and I'm going to ask you all about the others. So what is the correlation between what is the correlation between job commitment and intrinsic motivation? So what is the correlation between job commitment and intrinsic motivation? Can anyone tell me that? Can anyone give me the number? Can anyone give me the number of the correlation between job commitment and intrinsic motivation? Yep, 0.25, good job. And was that statistically significant? Was that correlation statistically significant? Yep, indeed it was. It was statistically significant. And we see that right here. This is where job commitment column intersects with intrinsic motivation row, correlation of 0.25 with a p-value that was less than 0.01. All right, so next one, what's the correlation between job satisfaction and job performance? Or sorry, I meant to say, what's the correlation between job commitment and job performance? So can anyone tell me the next one? What's the correlation between job commitment and job performance? Yep, negative 0.02, good job. And that is not statistically significant because there's no asterisks right there. It's not statistically significant because there's no asterisks right there. So yeah, negative 0.02. And the very last one, what's the correlation between intrinsic motivation and job performance? Yep, 0.17. And we see there's one asterisk there, so that is statistically significant with a p that's less than 0.05. Okay, if you're not getting this, that's perfectly fine. However, I would recommend rewatching this video after the lecture or asking me questions because this will be how many stats programs present your correlation results. This is how many stats programs present your correlation results. The stats programs expect you to be familiar with the correlation matrix, and they expect you to be able to look at this and very quickly say, all right, I see where this intersects with this, so I understand that's my correlation for those two variables, et cetera, et cetera. So once again, if you're confused by this, maybe rewatch this part of the video, maybe rewatch one of my prior lecture videos that I uploaded to Canvas. And in fact, I forgot to mention this before. I have sent y'all my YouTube channel that has my course lectures in it. The material we're covering now, I have previously taught an undergrad class that covers this. The undergrad class covers it over the course of an entire semester, whereas we're covering it over the course of, 3 weeks. So we're doing it a lot more quickly. We're actually covering a little bit more information in that course. But if any of the stuff that we're covering now to the end of the semester is confusing, try to find it in the undergraduate lecture videos I uploaded to my YouTube channel because we do cover a lot of this in those videos. Not everything, and once again, that class was over the course of an entire semester. So some of the stuff might be more drawn out, might be a little bit boring to y'all since that's at the undergrad level, but we do cover some of the same material in that undergrad class. Okay, someone asked, will the p-values be included in the statistic program? And the answer is yes for Jamovi, no for Excel. The answer is yes for Jamovi, no for Excel. However, with Excel, we can take the correlation and the sample size, and I'll show you a website. You just plug in the correlation and sample size, and it will give you the p-value. But Excel does not give it to you automatically. You have to use a different website to get a correlation p-value when using Excel, whereas Jamovi will automatically give it to you. So good question, very good question. Okay, any other questions, comments? Okay, last notes about a correlation before we take a brief break. 2 more notes is first off, correlations assume a linear relationship. So we talked about that before. I told you to remember that. And we looked at the scatter plots and we drew the straight line that best describes this data. We looked at pictures like this that looked at a positive correlation, a negative correlation, and then no correlation. So we looked at things like that. So therefore, correlation works really well if your data generally has a linear shape. Correlations are wonderful if your data has a linear shape. Or even sometimes a circle shape because that's no relationship. It works pretty well. But there are some instances where correlation does not work well. There are some instances you cannot assume a linear relationship. And this is an example of stats BS, where sometimes you'll see people give you a correlation and they don't give you access to look at the data. They don't give you access to look at the plots, the scatter plots. And if someone blatantly refuses to let you see the data, you should be skeptical. You should certainly be skeptical. And in fact, a lot of academic research is moving towards If you're to publish an article, you need to provide your data with the article. So therefore, people who read your article, people who review your article, could then go calculate these correlations and then test things like you see in these pictures right here to see if your analyses, were they appropriate or were they inappropriate. So as you see in these pictures, the interesting thing is all of those correlations, all those lines that represent the correlation, all 4 of those are the exact same. If you were to calculate a correlation on these 4 data sets, you would get the exact same correlation. These 4 data sets give you the exact same correlation. And as you see for the first one, that works pretty well. This first one works pretty well because this data generally has a linear shape, and you can assume a linear relationship between those 2 variables. But for the second one, that does not work well at all. This does not work well whatsoever. And it's because your data has a nonlinear shape in this example. The data has a nonlinear shape in this example. So therefore, if your data has a nonlinear shape, your correlation will still give you a result. You can still get a correlation coefficient. It's just not going to describe your data well. It's just not going to accurately describe your data. So therefore, when you calculate a correlation, you should first consider plotting your data. You should first consider creating a scatter plot and looking and seeing, oh, is my data generally linear? Or does it have this different shape? And maybe I should conduct a different type of analysis that doesn't assume a linear relationship between the 2 variables. And then the last 2 get at the same thought. This one right here, you can see that an outlier influenced this result, that this correlation should have been slightly smaller. This correlation should have been slightly smaller. However, you had an outlier that threw off your line, that made your line seem like there's a stronger relationship than there actually is. So correlations are also vulnerable to outliers. They're also vulnerable to outliers, that if you have an outlier in your data that can throw off your correlational results. And I've known many colleagues who have collected a data set, calculated their correlations, their regressions. They get so excited because they find these results that they think are groundbreaking. And it turns out all their results were simply biased by a single outlier, and the results are actually meaningless. And they have to go back and recalculate everything. And that's the same thing that happened in this last example, is that as you see, there should be no relationship because it should be a completely flat line. And flat line can also be vertical in addition to horizontal. So in this example, it should be no relationship, but you had this one single outlier that completely threw off the relationship and made it seem like there's a very strong relationship instead of no relationship whatsoever. So once again, when you're calculating correlations, consider making scatter plots, consider looking for outliers, consider looking for nonlinear relationships before you assume that your data has a linear shape without outliers. Okay. And then the second thing I wanted to say is that correlation does not equal causality. Just because 2 things are related does not necessarily mean that X causes Y. So just because 2 things are related does not necessarily mean that X causes Y. But there's a lot of things that could be correlated that don't necessarily mean that one causes the other. So one example that I'm sure that y'all have heard before is ice cream sales and murder rate. If you were to collect a data set of a certain demographic area or a certain regional area, you might observe a correlation that says as ice cream sales go up in that area, murder rate also goes up. Or maybe geographically, as this location or as a certain location starts to sell more ice cream, the murder rate goes up in that location. This is something that's pretty robust. You see this quite often. Does that mean that ice cream sales cause murder rate? Does that mean we need to prevent people from selling ice cream? The answer is obviously no. The answer is obviously no, that we cannot directly assume that ice cream sales cause people to go out and murder each other, that people are so driven crazy by ice cream that they just start stabbing everyone. Instead, what happens is there is a different variable that predicts both of these. There's a different variable that predicts ice cream sales, and there's a different variable that predicts murder. And it's typically, okay, one person said they didn't hear it before. I'm glad this is new to at least one person. So thank you for letting me know about that. Typically what that other variable is the temperature. It's typically heat. That in the winter months, murder rate tends to go down. In winter, murder rate tends to go down. And then of course in winter, ice cream sales tend to go down because it's cold. No one wants to buy ice cream. And typically with murder rate, it's assumed that people are inside more. There's less social interactions. There's less people causing friction with each other because you tend to be at home. You tend to be more isolated. So murder rate tends to go down in the winter. But when summer comes around, ice cream sales go up when summer comes around, and then also murder rate goes up. Also, murder rate goes up in the summer. Typically, it's believed because people are out more, they're interacting more, people are causing friction with each other. So it's actually temperature that predicts both ice cream sales and murder rate. So if you're to look at these two variables in isolation, yes, you would get a correlation between the two, but that correlation is because there's a different variable that predicts both of them. And if you're to account for that different variable, that correlation then disappears. If you're then to account for that other variable, that correlation then disappears. So therefore, ice cream sales do not cause murder rate, even though we can observe a correlation. This is a little bit tangential, but there is a really interesting article published, I believe, in a journal called Psychological Science that did argue that just when people are hotter, when people are warmer, they just get more aggressive. And the way they showed that is they looked at baseball seasons, and they showed that on games where it was hotter, there was more often to be, if you got hit by a pitch, if you're a batter and you got hit by a pitch, it was more likely that the other team would then retaliate against that. That it wasn't necessarily more people getting hit by pitches, there was more likely retaliation of hit by pitches when there was warmer weather. So there is some evidence to support that, all right, maybe just warmer weather causes people to get angry based on correlational results like that. And now there are becoming more experimental results where you bring people in a research lab, you crank up the temperature, and then you see, all right, is this person more aggressive? But that's a little bit tangential. Okay. Another thing to think about, and this is just something to ruminate on, is some people have argued this is also the case for job satisfaction and job performance, that people like to assume that happy workers are productive workers. People like to assume that the happier you are, the more productive you are, and that job satisfaction relates to job performance. But there are a lot of people out there that say, no, that's just a correlational result. We don't actually have evidence to support the causality between those two variables. We don't actually have evidence to support the causality between those two variables. So therefore, a lot of people say that that's just a correlational result that we cannot account for. And then last, there's a website that just calculates all these spurious correlations, which is correlations this person found that make no sense whatsoever. And just to support that, hey, just because two things are correlated doesn't mean they're causally related. And I would suggest you look at that because it's a really funny website. I really enjoy that website. And I'll leave it on the screen as we take a break. So if you come back from break early, look up that website. It's really funny the last time I checked. I hope this website hasn't changed since I looked at it because that would be really awkward. But hopefully it's the same website as when I taught this class last year. So, all right, let's take about a 8-minute break or so, and let's come back here at a little after, what time is it now? Sorry. A little after 7:30. Let's meet again a little after 7:30. So let's take a 6 to 8 minute break, and we'll come back a little after 7:30. So, and then when we come back, we will cover reliability and Cronbach's alpha, and then you'll have time to calculate analyses on your own time, and I'll be here to answer questions. So let's take a break, and then we'll meet back in about 6 to 8 minutes. Okay, it has been about 8 minutes, so I'm going to continue. Okay, so to wrap up my lecture today, I'm going to talk about reliability pretty briefly. I'm going to talk about reliability. First off, were there any questions about anything, just to check? Okay, so I'm going to talk about reliability. So first off, a lot of things we measure in business are done with scales. So things like job satisfaction, job performance might be measured by what we often call a Likert scale, or it's technically a Likert scale, but I hate pronouncing it Likert. I call it a Likert scale. Lots of people call it a Likert scale. So anyways, a lot of things we measure in business are done with Likert scales. So things like job satisfaction. I'm sure everyone here has taken a survey at some time in your life that told you on a scale from 1 strongly disagree to 5 strongly agree, how satisfied are you with your job? Or how satisfied were you with this professor? Or how satisfied are you with that meal? That's called a Likert scale. If you ever ask someone on a scale from 1 to 5, strongly disagree to strongly agree, or very little to a lot, et cetera, if it's any type of 1 to 5, 1 to 7, 1 to 9 type of deal, that's a Likert scale. There's a lot of things we measure in business with Likert scales. Job satisfaction, all the time we measure with a Likert scale because they're very easy to administer and they're very easy to analyze. It makes our lives a lot easier to measure things using this Likert format. We might also measure an employee's job performance using a Likert scale. So we might ask supervisors to, for each of your subordinates, rate their performance on a scale from 1, very poor, to 5, very good. Or on a scale from 1 to 5, indicate how much you disagree to agree with this statement. This subordinate is a good employee, disagree or agree. So there's a lot of things we measured using Likert scales. It's extremely important to show that our items used to measure a common construct are consistent or reliable. It's very important to show that our measures that extremely important to show that our items used to measure a common construct are consistent or reliable, because that gives us support that our measures are valid, that our measures can be used and they should be used. Because if you have a measure for job satisfaction or job performance that is not consistent whatsoever, then that means you cannot be certain about what you're measuring, that you do not have good reliability with what you're measuring. So you need to show that they're reliable. Okay, there are many different types of reliability that exist. There's inter-rater reliability, there's test-retest reliability. There are more than I can count types of reliability. But one of the most commonly discussed is internal consistency reliability. One of the most common methods of reliability, or one of the common types of reliability, I guess, is internal consistency reliability. And internal consistency reliability is the extent that items within a scale or a test are related to each other. So internal consistency reliability is the extent that items within a scale or a test are related to each other. And one way to think about this is if you're giving a Likert scale survey, you might have something like item 1, item 2, item 3. And once we'll learn later in the semester to perform analyses on that scale, we would average those 3 items together. To perform analyses on that scale, let's say that's a job performance scale, we would average those items together. However, calculating internal consistency reliability can provide you support that's appropriate. It can provide you support that is appropriate. So therefore, calculating internal consistency reliability will tell you, hey, this item 1, this item 2, and this item 3, all 3 of those are related to each other. All 3 of those have high internal consistency, hopefully, if you get support with your statistic. So based on that, if they have high internal consistency, that can give you support that you can average those together, and you can you can calculate statistics using that average of those 3 items. So in short, internal consistency reliability provides support that items within a scale are related, and then based on that support, that gives you justification to average those together and calculate analyses using those averages. And that's typically what we want to do, and that's typically what we will do throughout the semester. Okay. So from that, there's a lot of different methods to calculate internal consistency reliability. So first off, we could just calculate the correlations between all the items, but that would A, take a lot of time, and B, that would be really hard to interpret. Let's say if we have a 4-item scale, that would be 6 correlations between all those items. And it'd be kind of hard to say, all right, well, some of these correlations are small, some are moderate, some are large. Is that good? Is that bad? Can we support that? So it'd be really difficult to interpret our results, to interpret our internal consistencies, if we had to calculate the correlations between all the items. So to get around that, to make it simpler, to simplify that, for a long time researchers, one sec, sorry. For a long time researchers, there we go, would calculate what was called a split half reliability. For a long time, researchers would calculate a split half reliability. And in this method, we would take the average of one half of our scale items or test items and correlate it with the average of the other half. So if we had a 10-item scale, we would calculate the average of items 1, 2, 3, 4, 5, and then we would calculate the average of items 6, 7, 8, 9, 10, and we would just correlate average 1 with average 2. And then based on that, if that correlation was high, as you remember, 0.7 or above indicates that you're measuring the same thing twice. Typically, if you're calculating split half reliability, you want to get a correlation of 0.7 or above. So therefore, we would take our split half reliability indicator, the correlation of one half of our scale with the other half of the scale. And if it was above 0.7, we would say, hey, that supports our reliability. We're good to go. We can then look at this entire scale, calculate the average of the entire scale, and use that for analyses. All right, so that was certainly easier than looking at individual item correlations. So that's good. But does anyone see any concerns with this approach? Does anyone see any concerns with split half reliability? Anyone at all? I have faith in you. The individual items might not hold up. That's true. That is very true. So if the individual items might not hold up, that the overall average might be good, but the individual items might not work out. That is very true. That's also a concern with the other type of reliability we're going to be calculating. And there's other ways to investigate the individual items, but we're not going to talk about that in this class. That's something that you would cover in, let's say, our PhD program in the Mitchell College of Business. We're not going to talk about that in this class. So you're completely correct on that. We're just going to ignore that. So good answer. Does anyone else see any concerns with split half reliability? Anyone else see any concerns with split half reliability? Anyone else? I have faith in y'all.
Could it be the groups aren't really split evenly, like as far as what they're valued at?
Okay, so you said it could be the groups aren't split evenly. I think I'll take that. I will take that, and then yeah, I think that's correct. I think you're saying what I was wanting someone to say. So good job with that. That the groups might not be split evenly. Another way to think about that is that with split half reliability, there could be a lot of different ways you split the groups. So let's say we calculate split half reliability with items 1 through 5 and 6 through 10, and let's say we get a bad result. So let's say the correlation is 0.5, and we want it to be 0.7. Well, what happens if we then say, oh, what happens if we take items 1, 3, 5, 7, 9, and then 2, 4, 6, 8, 10, and correlate those? Well, maybe suddenly we get a correlation of 0.8, and suddenly our split half looks really good. Then maybe that we manipulate how we split the scale. Maybe we manipulate how we split the test. That, we might try to justify it as, well, the first time might have not done it evenly. Maybe we should have done it evenly this time. But regardless, there's definitely this concern with calculating split half reliability that it depends on how you split the scale. That sometimes you could split it one way and get a bad result, and then split it a different way and get a good result. And you just report the good result and pretend that's what you did the first time and hope no one ever calls you out on it. So therefore, a lot of researchers, I did not realize I put that way. Okay. So therefore, a lot of researchers looked into different ways to calculate reliability. Other researchers looked at different ways to calculate reliability. And I have listed on here that someone named Cronbach made a certain way. I must have had someone else type this up. Okay, because the fun fact about Cronbach's alpha, so let's X that out. The fun fact about Cronbach's alpha is that Cronbach did not make Cronbach's alpha. What actually happened is someone else wrote this paper in literally like 1900 that said, hey, split half reliability really sucks. We shouldn't use it. Here are some other methods we could use to calculate reliability. And in fact, that person, I think, provided 6 different methods. A few years later, Cronbach came out with a new paper that said, hey, this guy made this method to calculate reliability. I think that's really cool. I think that's a really good idea. We should start using that method to calculate reliability instead of split half reliability. And then based on that, everyone said, you know what, Cronbach, you're right. We should use that other guy's method. In fact, let's call it Cronbach's alpha because that's such a good idea. And then therefore it suddenly became known as Cronbach's alpha, even though Cronbach didn't create it. Cronbach just said, hey, this thing this other guy did is a really good idea. We should start using it. So it blows my mind every time I teach this that that's what happened with Cronbach's alpha, but that's what happened with Cronbach's alpha. Okay. So someone that was not named Cronbach, but Cronbach made it popular, made a method to calculate reliability to replace split half reliability. And what the Cronbach's alpha does, is through using a certain formula, which fortunately the stats programs we're going to be using, such as Jamovi, will calculate it for you. But through a certain formula, Cronbach's alpha calculates the average split half reliability of all possible split half reliabilities of a scale. If you go back and look at the original article, it's brilliant. This person makes this really elegant formula. It's not a brute force method. It's not just calculating it over and over and over and over and over and doing the averages. Instead, it's a really elegant formula that takes and gives you the average split half reliability of all possible split half reliabilities for a scale or a test. So that means it takes the average of the correlations between, let's say we're looking at a 6-item scale. If you take the split half of 1, 2, and 3 with 4, 5, and 6, and then 1, 2, and 4 with 3, 5, and 6, 1, 2, and 5 with 2, 5, and 6, that's messed up, but we'll continue. 1, 2, and 6 with 3, 4, and 5, 1, 3, and 4 with 2, 5, and 6, so on and so on. You take all possible combinations of the possible split half reliabilities and then average them together. That's what Cronbach's alpha gives you. So therefore, it eliminates this concern with cherry picking your split half reliability because it gives you the average of all possible split half reliabilities, which is brilliant. That's so amazing. That before you're concerned with, well, which one's the right split half reliability? What if someone's tricking me? Cronbach's alpha completely eliminates that concern, and it gives you the average of all possible split half reliabilities. So it gives you anything you could want regarding split half reliability, it gives it to you. So wonderful, a wonderful statistic, wonderful approach. There are some now other indicators of internal consistency reliability people are starting to like more than Cronbach's alpha, but it is still the dominant indicator of internal consistency. Cronbach's alpha is still the dominant indicator of internal consistency, so therefore we still use it all the time. Okay, and we call the statistic Cronbach's alpha. So therefore, if Cronbach's alpha is high, we can confidently say that our scale/test items are sufficiently interrelated. So because it's the average of all possible split half reliabilities, if Cronbach's alpha is high, we can confidently say that our scale or test items are sufficiently interrelated. And because we can interpret it similar to a split half reliability, which is based on correlation, typically we say that 0.7 is the minimum for okay reliability. Because like we said before, once you get to 0.7, you're starting to think the two things are measuring the same thing. You're starting to think these items are measuring the same thing in the case of Cronbach's alpha. But for Cronbach's alpha, we're really trying to get 0.8 and above because you really want to make sure all these items measure the same thing. You really want to make sure all your scale or test items measure the same thing. And to be certain about that, you really want your Cronbach's alpha to be 0.8 or above. Like someone in chat pointed out though, there might still be a chance that you have 1 or 2 items that are really crappy and the other items make up for it. So it could be that your other items are allowing your Cronbach's alpha to be 0.8, 0.9, even though you might have 1 item that's really bad that should be kicked out, just the other items make up for it. So Cronbach's alpha does not give you a guarantee that all of your items are good. It just gives you some support that this overall scale, that these items have sufficient internal reliability or internal consistency. So it's not a guarantee your items are good. It just gives support for internal consistency. That's all it does. And the last thing you should know about Cronbach's alpha is when reporting reliability, when reporting Cronbach's alpha, when reporting internal consistency, we usually include it on the diagonal of a correlation matrix. And you see this quite often. If we're looking at an academic article or we're looking at a practitioner report, if you see a correlation matrix and they have any number on the diagonal that's other than a blank or other than a 1, If it's anything other than a blank or other than a 1 on the diagonal, it's almost always the Cronbach's alpha. It's very often the Cronbach's alpha. So in this example, we just look at the diagonal and we see that where the first column intersects with the first row, that's the Cronbach's alpha for job satisfaction. So this is 0.85. So we would say the Cronbach's alpha for job satisfaction is 0.85. And therefore we would be satisfied with that. The job satisfaction scale had sufficient internal reliability. For column 2, where it intersects with row 2, we see the Cronbach's alpha is 0.91. Once again, we're happy with that. We would say that's sufficient internal consistency. That's a good Cronbach's alpha. This one's 0.79. This is for intrinsic motivation. So we would say the Cronbach's alpha for intrinsic motivation is 0.79. Once again, above 0.7, we're happy with that. And the last one for job performance is 0.83. So that's above 0.7. Therefore, we're happy with that. So in this example, all 4 of our scales had sufficient internal consistency. So therefore, we're happy with their Cronbach's alpha. These scales passed that necessary indicator for support. Let's put it that way. Okay. One thing I'll also note about this is statistics programs. If you ask for the correlation matrix, it will not automatically give you the Cronbach's alpha. For most statistics programs, if you calculate the correlation matrix, it will not automatically give you the Cronbach's alpha. Instead, you have to go through the menus. You have to do something different than the correlations to get the Cronbach's alpha. And that's okay. That's perfectly fine. So in practice, if you're writing this up for a practitioner report or a research article, typically you would have to make your correlation matrix first with all the other items, and then go back and calculate your Cronbach's alphas and then add them to your correlation matrix. Okay, so that is all for Cronbach's alpha. Are there any questions about anything at all we covered today? Any questions about anything at all? This is for inner item reliability, has nothing to do with item validity. Interesting, good question. So the question is, this is for inner item reliability, but has nothing to do with validity. So those are different concepts. You're completely correct. Those are indeed different concepts. So reliability is not the same as validity, but you cannot have a valid scale that is not reliable. So reliability is different than validity, but you cannot have a valid scale that is not reliable. And that is indeed important. So I'll talk about this for a minute. One way to think about this is think about a bullseye. Think about a bullseye, and this bullseye is the construct we're trying to measure. And each item is a dart we throw. Each item is a dart we throw. If we have a scale that has high validity and reliability, that means all of our darts are really close to the bullseye. If something has high reliability, all the darts are thrown close together, and they're all close to the bullseye if it has high validity too. So here's another example. We might have a bullseye. Our items we can think of as a dart, and I'll use a different color this time. In this example, we might have darts that are thrown everywhere. In this example, that means the darts that are thrown everywhere, they have poor reliability. This is how you can think of something with poor reliability. It's just the darts are thrown everywhere. In this example, good reliability, they're all close together, they're all interrelated. In this example, bad reliability, all these darts landed at very different locations. So in this example, because we have bad reliability, we also have bad validity. We also have bad validity because these darts are nowhere close to the bullseye. They're all over the place. However, reliability and validity are different because you might have this last example where we have a bullseye. And this is important, so thank you for asking the question, and thank you all for those who are still listening. In this last example, we might have high reliability. We might have high reliability, but in this case, we would still have low validity because even though all of our items are close together, even though they're really internally consistent, we miss the bullseye altogether. We miss the bullseye altogether. So in this example, we have high reliability, but low validity. In this example, we had low reliability, and therefore we had low validity. And then in this example, we had high validity and high reliability. So very good question. Very, very, very good question. And that's something that if you were to enroll in the PhD program in the Mitchell College of Business, I teach a class where this is my jam. I know that's weird to put, but this is something that I get super excited about. Like a lot of my academic papers talk about this concept. have gotten into arguments with people because they produced measures that they claim have high reliability and high validity. And then when you go back and look, they came nowhere close. And I literally have papers where I'm calling out people saying, no, like you did it wrong. You have poor validity, you have poor reliability. We get into these weird academic catfights and no one really cares except just us two, but that's how academics works. So yeah, psychometrics, exactly. This is all psychometrics. The class I teach in the PhD program is exploratory factor analysis, confirmatory factor analysis, and structural equation modeling. Structural equation modeling kind of being outside the realm of psychometrics, but EFA and CFA certainly in the realm of psychometrics. And that's what this reliability, validity stuff is all about. So glad you know about that. Very glad you know about that. It's fascinating stuff. So if anyone wants to talk to me about psychometrics, I will talk about it all day long, every day, etc., etc. Okay. Any other questions? Any other comments? Going once, going twice. Okay, and then the closing thought I'll have with reliability and validity is if you're interested in personnel selection is all about reliability, validity, and utility. So if you're interested in personnel selection, if you're in HR, for instance, that's what all personnel selection is about. So lots of important stuff. Okay, so as I said, to close out class, I'm going to give you all an opportunity to, so I'm going to stop share. Okay, I'm going to give you the opportunity. I sent out those guides on mattchauer.com. I want you all at your own pace to see if you can calculate correlations in Cronbach's alphas using those guides I send in my email, and I will be available for any questions. I am going to turn off my camera because I think that would be terribly awkward if I just sat here for 30 minutes with the camera on. So I'm going to turn off my camera, but I will have chat open. So just send me a message. I'll try to respond immediately. But I might take a minute or two. I might get up and go do something else for a minute. But just send me a message if you have any questions. I'll hop right back on or answer anything. But otherwise, you could just leave. You're free to go. You're free to do anything else. And you're free to go do your own thing. So go ahead, start on those guides. Just now, thank you for that. I am meeting with one group, so I'm happy to meet with that group right now. We'll go ahead and do that while everyone else is getting started. But go ahead and get started if you want to, or leave. But I'm going to be here for questions for the next 30 or so minutes, and I'm happy to answer anything. So yeah, go ahead, get started, and then let me know if you have questions. And for the group that wants to chat with me, if y'all are okay with it, I would be willing just to have the chat right now in this open chat room, if y'all are okay with that, or we can try to figure out something else, whatever y'all want. Okay. Yeah, so y'all want to be pulled into a room? Yeah, so send me the names of the people in the private chat, and I will pull y'all into a breakout room, and I will join the breakout room. And then for anyone doing the analyses, I'll hop back in here after I'm done talking with the group. So yeah, so just send me the name of the people, and I will assign y'all to a breakout room. Okay, so we have Aaron, Courtney, okay, so y'all sent me a list of, are all of y'all here? Okay, so yeah, I don't know if you're all here. Okay, so I see 3 of y'all. Okay, I'm going to invite y'all to the room. If you're in the group that and I didn't invite you, please let me know and then I'll invite you. So I invited all the members to the group to the breakout room. If you're in that group and I did not invite you, please let me know and I will then invite you to the breakout room. Okay, so I'm going to join that other group and then I'll come back to this when I am done. All right, I am back in the main room. I don't know if anyone sent anything to chat when I was gone, but I do not see anything new in the chat. So if you put anything in the chat while I was just now gone, I do not see it, so please copy and paste it. Yeah, but otherwise I'm gonna mute, I'm gonna stop my video, and I'll be back for the next 15 minutes. I'll be back and forth. Give me 1 sec to look at that. I'll look at that really quickly. Okay, someone in chat said they did the Cronbach Alpha guide and they got a Cronbach Alpha of 0.863 instead of 0.85. That is also what I got. So I have no idea why my guide that I put online is different. I must have actually uploaded the wrong data set. So yeah, so I got the same answer. I got 0.8626. So I will have to update that. So if you do the Cronbach Alpha guide and you get a Cronbach Alpha of 0.8626, then that is correct.
I think my data must be wrong then, because I used the same Excel sheet and turned it into a CSV, and my numbers must have been way off then.
Yeah, if you, let me look up and see. I think the Excel sheet, is that the same? Downloads. The Excel sheet might be, maybe that's why I got this different thing. Yeah, I think the Excel sheet is a different data set. Yeah, the correlation sheet is a different data set. So if you're doing the Cronbach Alpha guide, you'll have to download the Cronbach Alpha data set.
Ah, well, that makes sense. Okay.
Yeah, so yeah, to get the Cronbach Alpha data set, it's in the body of the Cronbach Alpha and Jamovi guide, which I'm now really bothered that it has the wrong answer. I have no idea why I got the wrong answer. So someone said on the test, can we just use Excel or do we need to use Jamovi? So the test could ask you for Cronbach's alpha. That's something I think would be reasonable to ask on a test. And Excel cannot calculate Cronbach's alpha. So if you're okay with missing that question, then you can just use Excel. But if you want to get that question correct, you would also need to use Jamovi or any other stats program that can calculate Cronbach's alpha. For instance, SPSS can. So on the day of the test, you could come to campus and use a lab computer that has SPSS on it or should have SPSS on it. So if you're uncomfortable with using Jamovi, there is SPSS. There's also another free program called R. I have taught this class using R before. I have guides for R that can also calculate Cronbach's alpha. So if you would rather use R, that's also available for you to use instead of Jamovi, for instance. So long story short, Excel cannot calculate Cronbach's alpha. So if you want to get everything correct on the test, you would either have to use Jamovi, SPSS, or R in addition to Excel. Okay, and thank you for making me aware that, oh, I think the person left. Yeah, so I fixed the Cronbach's alpha guide, so the Cronbach's alpha guide should be correct now. So Cronbach's alpha guide should be correct.